In the last session, we had learned about weighted least squares. We have seen that weighted least squares is a natural progression from ordinary least squares, where instead of minimizing the residual sum of squares, we introduce a weight matrix and minimize the weighted residual sum of squares, if we can say so. In doing that, we have learned about using the sandwich estimation procedure and the robust estimation techniques. But nowhere we had assumed the final assumption about the distribution of yi, which is one of the assumptions in the general linear model. In this session, we shall be using the distributional assumption. So basically, we would be using a likelihood based approach to find the estimates or the estimator of beta, that's the parameter of interest, and we shall be seeing what are the properties of it. In the process, we shall learn about something called the restricted maximum likelihood. So restricted maximum likelihood is a concept which has been common in use of general statistics, and here we shall elaborate on that and we shall see what are the properties of restricted maximum likelihood estimators. For a general linear model, y is assumed to follow a multivariate normal distribution with the mean x beta and the variance covariance matrix capital V. And if we assume that the design is complete and balanced, then capital V is block diagonal sigma square V naught. Now, if we assume that V naught is known, then the weighted least squares of beta we have already learned in our previous session would be beta hat V naught, because V is characterized by V naught, and that is x transpose V inverse x inverse x transpose V inverse y. Now the log likelihood in this case is a function of beta sigma square and V naught, and it comes out to be minus half n into m log sigma square plus m log determinant of V naught plus 1 by sigma square y minus x beta transpose V inverse y minus x beta. Now, if we substitute beta hat V naught, because we know what exactly is beta hat V naught under weighted least squares, we can see that the maximum likelihood is now a function of sigma square and V naught, and it is minus half nm log sigma square plus m log determinant of V naught plus RSS based on V naught by sigma square, where RSS V naught is y minus x beta hat V naught transpose V inverse y minus x beta hat V naught. Now, if we find the maximum likelihood estimate for sigma, it comes out to be sigma hat, again a function of V naught, which is RSS V naught by Nm. Now, if we substitute beta hat V naught and sigma V naught, so we started with beta, sigma and V naught, then we substituted beta hat V naught and obtained the estimate of sigma hat V naught, and now we are substituting beta hat and sigma hat in the log likelihood, and the remaining log likelihood would be a function of the unknown V naught, and that comes out to be, if I write L V naught and there is a suffix P, the P suffix stands for profile. So what we get is called the profile log likelihood, and that is minus Nm by 2 log RSS V naught minus m by 2 log determinant of V naught. If we maximize the profile log likelihood, we get the MLE of V naught. Once we have the MLE of V naught, we can plug in back the estimate for beta hat V naught and sigma hat V naught. So that becomes beta hat V naught hat and sigma hat V naught hat to be estimates of beta and sigma or sigma square. However, there is a complication, and the complication is that the maximization with regard to V naught requires numerical optimization techniques, and often it's difficult that such numerical optimizations converge to a single value. And even more than that, there is another issue, and the issue is that the MLE of the variance components or the maximum likelihood is biased. So this introduces us, or this motivates us to use something called the restricted likelihood, a restricted maximum likelihood estimator, or the REML estimator is what we see. Now, before introducing to the concept or the formal definition of REML estimators and their properties, let's consider two simple examples to illustrate what exactly is REML estimator, what are we doing for REML estimator. See, the idea of residual maximum likelihood estimators was, it's not that it had not been learned previously. We have learned that, although we didn't know at that point of time that it was REML that we are using. For example, take the simple regression equation, or take the case where we have a series of observations where y equal to y1, y2, yn, and they are IID normal with mean mu and variance sigma square, and our task is to find the estimates of mu and sigma square. The simplest answer is that, or the estimate of mu is y bar, the maximum likelihood estimate of mu y bar, and the maximum likelihood estimate of sigma square is residue RSS by n, where RSS is summation yi minus y bar whole square. Now this is fairly common, and we have done this in the maximum likelihood estimation classes or what inference, basic elementary inference classes. But associated with these two facts is also the fact that y bar is unbiased, but sigma hat square is biased. Now to make sigma hat square unbiased, what one does is simply adjust the error degrees of freedom and gets the unbiased estimator, which is RSS by n minus 1. So we start with a biased variance estimator, which is RSS by n, and then we adjust it to get an unbiased estimator, which is RSS by n minus 1. Now in the one-dimensional case, this is what we get, and we can extend it for the two-dimensional case. Say for a multivariate case, where suppose we have a linear model where y follows normal, multivariate normal, x beta, sigma square in. Again, beta hat MLE is unbiased, and we know that the beta hat MLE comes out to be x prime x inverse x prime y, where sigma hat MLE is RSS by n, and sigma hat MLE is biased. But we can adjust for the degrees of freedom. In the univariate case, it was n minus 1. Here it is n minus p, and the unbiased estimator of sigma hat square comes out to be RSS by n minus p. Now keeping these two examples in mind, we formalize the definition of restricted maximum likelihood. Assume that y follows multivariate normal x beta capital sigma. The REML estimator is defined as the maximum likelihood estimator based on a linear transform y star. So instead of obtaining the estimator from y, we are obtaining the maximum likelihood estimator of y star, where y star is defined as AY, and A is so chosen that the distribution of Y star is independent of beta. Now, what is the idea? The idea is to separate the part of the data into two parts. I mean, the total data into two parts. One part is the data used for the estimation of V, that's the variance components. And another part is the data used for the estimation of beta. So now formalizing, we can say that the REML estimator is defined as the maximum likelihood estimator based on a linearly transformed data set Y star equal to AY, such that the distribution of Y star is independent of beta. Now to investigate the properties, assume A is I minus X transpose X inverse inverse X transpose. Note that the latter term X transpose X inverse inverse X transpose is called the hat matrix. Now rank of A is Nm minus P. And this is the matrix, if we remember correctly, this is the denominator for the residual sum of squares. This Nm minus P. Okay, so what is happening here? Assume that B is a matrix of order Nm into Nm minus P, such that A is equal to BB transpose and B transpose B is equal to identity. Define Z equal to B transpose Y. If we do that, then expectation of Z comes out to be 0 and covariance of Z and beta hat is also 0. Here I am not giving the proof, but the proof is given in the accompanying document of this video. And the proof is essentially simple. The only thing is that it needs to the expectation, the variances and expectations to be used for Y, and one can do that. Just put in the variance and the expectation and it simply comes out to be 0. So the proof is given there. So the idea is that Z hat and beta, so Z and beta hat are independent. Now if we see the distribution of Z and beta hat, so Z is By and beta hat is some G into Y, then Z and beta hat is a linear transformation in Y, and so the joint density is f of Z beta hat, which is equal to 1 by determinant of J or Jacobian of determinant of J Fy, which can be written as Hz into G beta hat because they are independent. We have proof that Z and beta hat are independent, and J is the Jacobian independent of the parameters. Now what happens? Hz, now if we just use this, then Hz is Fy by determinant of Z G beta hat. And what is the distribution of Hz? It can be shown that if we use the distribution of beta hat and the distribution of Y hat, so Y follows a normal distribution with X beta and variance is V, while beta hat follows a normal distribution, and if we remember from our WL weighted least square class, the session, that beta hat is unbiased, so this is normal beta, and X transpose V inverse X inverse is the variance of beta hat. So it again follows a normal, so if we just put in the values, it comes out that Hz can be defined or comes out to be E exponential of minus half Y minus X beta transpose V inverse Y minus X beta hat, determinant of J, determinant of V to the power half, and then determinant of X transpose V inverse X to the power half, 2 pi to the power mn minus p by 2. The most important thing here is to see that we started with Z, which is B transpose Y, where A is B transpose. But the density of Z is free of A. And it is from this density of Z that we get the REML estimator. So the REML estimator V hat, and then we write REML maximizes log of HZ, which is LRV. And it can be shown that the maximum likelihood maximizes the profile log likelihood. So if we obtain the maximum likelihood estimator of the variance, it maximizes the profile log likelihood, which is LPV. And this LPV is nothing but LRV plus half log X transpose V inverse X. So that means the profile log likelihood is LRV, the log likelihood for obtaining V, and that's the REML plus half log X transpose V inverse X, and this is the part from which beta hat is obtained. So to summarize the properties of REML, what do we get? We get that REML estimator of variance components does not depend on A. REML estimates of variance components are unbiased. Once we get the estimate of variance components, we can get the estimates of the parameters, and one way of doing that is to plug in the REML estimates of the variance components. The moment we use the REML estimates of the variance components, plug in the REML estimates of the variance components to get the parameter estimates of beta, we call it as REML estimate of beta. Now REML is asymptotically equivalent to maximum likelihood. The maximum likelihood and REML estimates of beta are different, because obviously in beta, for the maximum likelihood of beta, one uses the variance components obtained from maximum likelihood, while for the REML estimates of beta, the variance components obtained from REML is plugged in. But that difference is often not very substantial. In this session, we have learned about restricted maximum likelihood estimates. We started with maximum likelihood estimates in context to a general linear model, and then saw the need of using restricted maximum likelihood estimates, which basically separates the data into two parts, and the one part of the data is used for estimates of the variance components, and one part of the data is used to estimate the parameters. The advantage of using restricted maximum likelihood estimates is that the resulting estimators are unbiased, while for only maximum likelihood estimates, the variance components that are obtained, or the estimators of the variance components that are obtained, are not unbiased. They are basically biased. So we have started in this 3 series, we started with the general linear model, which we showed as a natural progression of the linear model, and or rather I would say that a natural progression from the ordinary least squares. And then we talked about weighted least squares and robust estimation principles and strategies. From there, in this session, we talked about the maximum likelihood techniques, and then again went into something called the restricted maximum likelihood technique.